Hello, welcome to Module 12 of the course on application of spectroscopic methods in molecular structure determination. We are continuing the lecture from Module 11 on the use of NMR spectroscopy in stereochemistry determination. In this module, we will consider the nuclear Overhauser effect, how it is used for determining stereochemistry of organic compounds, and also look at some aspects of the lanthanide shift reagent, how they are used for determination of stereochemistry of organic compounds. Now, we have already introduced the concept of nuclear Overhauser effect in the earlier lectures, so let me just refresh your memory. Nuclear Overhauser effect is defined as the change in the intensity of one spin when another spin transition is perturbed from the equilibrium population. What is important here is that the nuclear Overhauser effect essentially depends on the close proximity of nuclear spin. In other words, if two hydrogens, one of the hydrogen has to be observed under nuclear Overhauser effect conditions, it has to be in close proximity to the other hydrogen, then only it is possible to observe the effect of nuclear Overhauser effect on these nuclear spins. Therefore, the distance relationship essentially gives important information about the three-dimensional molecular geometry. So, based on the nuclear Overhauser effect, one can determine the molecular geometries fairly simply. The nuclear Overhauser effect observed for a spin I when spin S is perturbed is given by this expression. This eta I is the nuclear Overhauser effect when the spin I is observed and the spin S is saturated. This would be essentially the difference between the intensity of the signal in the absence and in the presence of nuclear Overhauser effect. I is the intensity in the presence of nuclear Overhauser effect, and I0 is the original intensity in the absence of nuclear Overhauser effect, divided by the intensity in the absence of nuclear Overhauser effect times 100 gives the percentage observed nuclear Overhauser effect in terms of this expression. Now, therefore, it is necessary to measure the spectrum under the nuclear Overhauser effect condition as well as in the absence of nuclear Overhauser effect. In order to be able to ascertain the nuclear Overhauser effect being felt in the spectrum, it is necessary to obtain a different spectrum. In other words, you record the spectrum under the conditions where the nuclear Overhauser effect will be present, and record the spectrum once again under conditions where nuclear Overhauser effect will be absent. Take the difference spectrum that corresponds to the NOE difference spectrum. Now, the pulse sequence for the NOE difference spectrum is given here. The top one is the spectrum accumulated under the conditions where NOE is present. The bottom one is under the conditions where no NOE will be present. In other words, this will be the control experiment. The way it is done is, initially, let us say we have two hydrogen. We want to observe the hydrogen A under the irradiation of hydrogen B. Then this would correspond to applying a frequency of hydrogen B under these conditions before the pulse of the hydrogen A is being set up. And this will essentially saturate the hydrogen B and set up the nuclear Overhauser effect corresponding to the transfer of spin polarization from hydrogen B to hydrogen A. Then the hydrogen A is excited and the free induction decay is observed. In the case where the control experiment is done, it is not exactly the hydrogen B frequency that is being applied. Off resonance radiation means that the frequency is not matched. It is offset by a few hundred kilohertz or so in terms of the frequency difference between the actual frequency and the applied frequency. This will not saturate the signal and it will not essentially give you the nuclear Overhauser effect either. And under this condition, when the spectrum is accumulated, this would be a spectrum without the nuclear Overhauser effect. So, if you subtract these two spectra, the different spectrum will essentially tell the effect of nuclear Overhauser effect, and that is how the nuclear Overhauser effect different spectrum is normally recorded. Now, let us consider a simple example of the normal spectrum which is being recorded for this particular sample. This is a azide derivative, and in this particular compound, the bottom trace is actually the control 1D experiment. In other words, this is a normal one-dimensional NMR spectrum of this particular compound with the peaks assigned to various hydrogens in this particular molecule. Now, if you look at the hydrogen number 2, it comes at the highest delta value because it is corresponding to a hydrogen bearing on the carbon bearing an oxygen as well as a carbonyl functional group. This is an ester functional group, and this is around 4.65 ppm or so. And the second trace is actually a difference NOE spectrum. In other words, Under the conditions of irradiation of 2, the molecule is observed, and with and without NOE effect it is observed, and this spectrum is essentially subtracted from the one with the NOE to get the different spectrum. So this is a different spectrum after subtraction of the two spectra accumulated in this manner for this particular molecule. So you don't see these peaks here because they don't have any changes from the normal spectrum or the control spectrum and the one with the NOE. In other words, these hydrogens do not undergo any kind of an NOE effect. The only hydrogens that do show the NOE effect by means of an enhancement in the different spectrum is essentially hydrogen on carbon number 3 and hydrogen on carbon number 5. In other words, this is actually syn. This hydrogen here is syn with respect to the hydrogen in this carbon and also the hydrogen in this carbon. So the spatial close proximity between this hydrogen and this hydrogen makes the NOE to be observed maximally for this particular combination of hydrogen, namely hydrogen at the position 2 and hydrogen at position 3. These are cis hydrogens. Essentially a large nuclear Overhauser effect is what is observed. Hydrogen 2 and 5 are also cis with respect to each other, and you do see a small nuclear Overhauser effect, enhancement effect that is seen by means of a positive peaks in this particular case. Since 2 is saturated, you don't see the signal for 2 and you don't see the signal for 4, 6 and 6 prime, essentially because they don't have any nuclear Overhauser effect as it's seen in the different spectrum. So this essentially tells you that the relative stereochemistry between 2 and 3 must be cis with respect to each other. Similarly, the relative stereochemistry between 2 and 5 also must be cis with respect to each other. The relative stereochemistry between 2 and 4 is actually trans, and that is the reason you don't see any nuclear Overhauser effect for the proton at carbon number 4 in the different spectrum. The top trace again is by irradiation of the hydrogen at carbon number 3. Carbon number 3 also has a cis hydrogen with respect to carbon number 2 and 5. So one should observe the nuclear Overhauser effect corresponding to carbon number 2 and carbon number 5 when 3 is irradiated. In other words, the hydrogen on carbon number 3 is irradiated. One does see the effect on hydrogen on the carbon number 2 and 5 because they are cis with respect to each other. So this clearly demonstrates the relative stereochemistry of this molecule to be 2 and 3 being cis, 3 and 4 being trans, and 4 and 5 being trans. 2 and 5 as a result is also cis with respect to each other. So the stereochemistry determination is this molecule is essentially done by the difference in the nuclear Overhauser effect spectrum. Cis and trans geometry around a double bond is possible to obtain the stereochemistry information if there is a coupling between the two partners, cis and trans coupling is present. However, if there is only one olefinic hydrogen, how does one observe the stereochemistry of the molecule is the question. Now, under these conditions, nuclear Overhauser effect difference spectroscopy is employed in this particular case. You can look at this hydrogen here. This is the only olefinic hydrogen present in this molecule. So it should be possible to pick this hydrogen and irradiate the hydrogen. Under the conditions of irradiation of this hydrogen, there is a 6% enhancement of the signal of this particular position hydrogen. So that indicates they are cis with respect to each other. In other words, there is no enhancement of this particular signal in the NMR spectrum. Similarly, when this particular methylene is irradiated under the conditions of nuclear Overhauser effect, difference spectroscopy tells that there is a 10% enhancement in the hydrogen signal for this particular hydrogen. So one can mutually saturate either this hydrogen or this hydrogen and observe the relative nuclear Overhauser effects in the different spectra. If you take the opposite isomer, when this hydrogen is irradiated, there is no enhancement here. However, when these two groups which are cis with respect to each other, they are mutually irradiated one after the other, there is a 4% nuclear Overhauser effect in this direction and 6% nuclear Overhauser effect in the other direction. So this essentially tells that this is the compound where the the hydrogen and the silyl groups are trans with respect to each other. This is a compound where the hydrogen and this silyl group are cis with respect to each other. So in the absence of a vicinal coupling between the two partners of a olefinic hydrogen cis and trans, it is possible to obtain the SDE stereochemistry of the molecule based on nuclear Overhauser effect and the difference spectrum, where the differences in enhancement can be very clearly seen between these two isomers. The same is true when you want to determine aromatic substitution. This is a 1,5 disubstituted imidazole. In other words, this is 1, 2, 3, 4, 5. This is a 1,5 compound. And if you look at this particular isomer, this is 1, 2, 3 and 4. So the regioisomers are different in this particular case. In this case, the two substituent, the nitrogen substituent and the carbon substituent are on the adjacent position, whereas in this case the nitrogen substitution and carbon substitutions are not on the adjacent positions. So this is a 1,5 disubstituted imidazole and it's a 1,4 disubstituted imidazole. What is interesting about this system is that when you do irradiation of this particular hydrogen, which is easy to pick because this is the highest chemical shift value hydrogen in the molecule, and these are the two aromatic hydrogens present in this molecule, so you can easily pick out these two hydrogens very easily in the NMR spectrum. And when you irradiate this particular hydrogen, there is a nuclear Overhauser enhancement of the CH2, which is flanked by nitrogen and oxygen. This would be probably the highest chemical shift value of hydrogens in the aliphatic region. So this enhancement can be very clearly seen. And when this hydrogen is irradiated, the enhancement of the signal corresponding to this CH2 can be very easily observed. On the other hand, if you do the two position hydrogen irradiation in this molecule, that results in the enhancement of this particular signal, whereas when you irradiate the other hydrogen, that has an enhancement of both this methylene as well as this methylene, because both the methylenes are adjacent positions with respect to this particular hydrogen. So here for this hydrogen you see only one enhancement, whereas for this molecule this hydrogen irradiation gives enhancement of this CH2 as well as this CH2, clearly telling that these two substituted positions are with respect to this particular hydrogen in a 1,2 fashion substitution that corresponds to the 1,4 disubstituted imidazole. This corresponds to 1,5 disubstituted imidazole. Now one can use the nuclear Overhauser effect enhancement effect in very effectively when you talk about this kind of fairly complex bicyclic system, for example. This is a cis-decalene system. In the cis-decalene system, this hydrogen and this hydrogen relative stereochemistry is established based on the coupling constant. This is essentially trans-diaxial kind of a coupling, so it is a high value in terms of large value of the coupling constant, whereas this is a axial equatorial kind of a hydrogen coupling, and that corresponds to about 4.2 Hertz, and this corresponds to about 13 Hertz or so. So based on that, the skeleton of this molecule is determined to be a cis-fused decalene system. Not decalene system, this is a ASA decalene system, for example, and the relative stereochemistry of these two hydrogen is also decided based on the coupling constant information. Where the coupling constant information is very difficult to come by, it is also possible to use the nuclear Overhauser effect. Let us take this example here. This is again a bicyclic fused bicyclic molecule, and this is a cis fusion is what we are talking about in this particular case also. When the red hydrogen is irradiated, it is in close proximity with this axial hydrogen, which is a 1,3 diaxial, and this equatorial hydrogen, which is a 1,2, this again an axial type of a system. This is a cis hydrogen. This is also a cis hydrogen. So one observes a nuclear Overhauser enhancement of 3 different hydrogens when the red hydrogen is irradiated in the molecule, essentially establishing the relative stereochemistry between these two centers and these two centers also for this molecule. Now let us see how one can determine, for example, ratios of enantiomers, because enantiomers are indistinguishable in the NMR spectroscopy. So if you want to see different signals for enantiomers in the NMR spectrum, you need a chiral solvent, which is too expensive to employ. On the other hand, if one makes a salt or a ester derivative of an enantiomeric mixture, in this particular case this enantiomeric mixture of alcohol if you take, and treat it with a chiral acid chloride, which is also enantiomer, these two combinations essentially will 4 different isomers. These two are enantiomers in nature, and these two are diastereomeric mixture in nature. So enantiotopic protons are isochronous, in other words they have the same chemical shift, whereas stereotopic protons are anisochronous, in other words they show different chemical shift value in the NMR spectrum. Let us assume for the time being that we are taking only the R isomer of this particular acid chloride, which is called Mosher's ester chloride. Then we will have R of the blue, red of the other one. So red R and R combination will be there, and R and S combination also will be there. In other words, the blue R and the red S combination will be there. So those are diastereoisomers, and they can be readily distinguished by NMR spectroscopy. This is what is illustrated here. The R acid chloride, namely the acid chloride is taken only R isomer, and a racemic mixture of this particular alcohol is taken and the ester is formed. The resulting ester gives you nicely two different signals for this particular hydrogen here. This hydrogen, which is a tertiary hydrogen here, which is adjacent to the in other words, let us take this methyl group. This is a methyl region is what we are looking at. These two peaks are corresponding to the tertiary butyl functional group in this molecule, and this corresponds to the CH3 functional group in this molecule, for example. If you take the alcohol alone, this will simply give a doublet for this hydrogen, this methyl group, because it is split by this hydrogen into a doublet, and this also will give only one kind of a tertiary butyl group corresponding to a mixture of enantiomers. On the other hand, when it is reacted with an active acid chloride and this is formed, this ester is formed. This is a diastereomeric ester. You have the R acid chloride and racemic alcohol. So you will have RR combination and RS combination, and that corresponds to two diastereomers being present. The two diastereomers are easily distinguished. This is identified. This CH3, which was originally a doublet because of the hydrogen, now two doublets are seen, one corresponding to the RS isomer, the other one corresponding to the RR isomer. So if one integrates these peaks, one can easily identify how much of RR and how much of RS is present in this molecule, which in turn can tell you about the enantiomeric excess or enantiomeric ratio of the two molecules. Since we have taken a racemic alcohol, the ratio is nearly 1:1 in this particular case. Similarly, the tertiary butyl group is also taken as the RR and the RS isomer. Each one gives a singlet for the tertiary butyl functional group, and from this integration also one can tell that we are dealing with the racemic alcohol of compounds in this particular case. Now this is a 60 MHz NMR spectrum of the plus isomer of the Mosher's ester of racemic phenyl tertiary butyl carbonyl. In other words, this is the compound essentially, and this is essentially the difference is that you have a methyl group here, whereas this is a phenyl group here. That is a difference. So the pure isomer plus isomer of the ester and the pure plus isomer of the alcohol is shown in the inset here. Let me just see. For example, this is a racemic mixture of alcohol with the acid chloride, and this is one of the pure enantiomers of the alcohol. You can see here one of the diastereomer corresponds to the alcohol plus alcohol, which is over here, and the other diastereomer, which is not present in the pure plus alcohol, is missing in this particular case. So the enantiomerically pure alcohol gives only one peak. The enantiomerically not pure, in other words, the racemic mixture of alcohol gives two peaks corresponding to this particular signal. There is no coupling partner to this hydrogen, so it is a diastereomeric mixture of esters is what is formed when it is treated with the Mosher's acid chloride, for example. So the example here essentially illustrates the fact that the Mosher's esters can be formed using this acid chloride alcohol reaction. When it does so, if you take a pure Mosher's acid chloride and a racemic mixture, it will give a diastereomeric mixture of esters which can be easily distinguished. Enantiomers cannot be distinguished, but diastereomers can be distinguished easily by NMR. That is the basic principle behind the technique that is being used. And the one advantage of Mosher's salt or the Mosher's ester is that the diastereomer signals are fairly well separated, as you can see. So the integration of the signals and hence the ratio determination becomes easy. Not only that, one can use also fluorine NMR to look at the CF3 group in these compounds. That is also possible to distinguish, that is also useful to distinguish or get the enantiomeric excess ratio of these compounds in the molecule. This is another example of a racemic mixture is taken and a pure S isomer is taken with the R isomer of the Mosher's ester. In other words, R isomer of Mosher's acid chloride is reacted with the racemic alcohol here and a pure S alcohol in this particular case. R and S denotes the absolute stereochemistry, please recall, and otherwise refer to the Nasipuri book as to determination of the absolute configuration of these centers in these molecules. So in this particular case, the olefinic hydrogen appears in this region. In the racemic mixture, of course, there will be two isomers corresponding to the RR and the RS. Here R and S configurations are there. Here only R configuration is there. So RR combination and RS combinations are diastereoisomers. They will give two different peaks in the NMR for this particular hydrogen. Similarly, this hydrogen, which is bearing the ester functional group, that also comes as two isomers. So integration of this peak essentially tell you how much of the R alcohol and how much of S alcohol is being present in the system. as far as the enantiomeric enrichment is concerned or enantiomeric excess is concerned. In the case of the pure RS isomer, this is only one enantiomer that we are talking about, so it gives only one peak. So this peak, which is coming around 6.5 or so and 6.6 or so, this peak here essentially corresponds to this peak here, and this peak here, which is 5.57, and this is around 5.57, essentially corresponds to the S isomer. So one can assign these tall peaks to the S isomer of the alcohol and the small peaks to the R isomer of the corresponding alcohol. Now we have also seen the effect of lanthanide shift reagent on chemical structures when it coordinates to certain Lewis basic sites in the organic molecule. This is familiar to you already. This has been introduced. This is a Mcconnell equation. It depends on the angle of the coordination site to the europium to the hydrogen under observation divided by r cube. Since there is a distance relationship, since it is varying with respect to the power 3 of the distance, it rapidly falls off as the distance moves further and further away from the europium complexation center. This is nicely illustrated in the determination of stereochemistry of these two isomers. If you look at this molecule, there is a chiral center here and there is another chiral center here, but these two isomers are diastereoisomers. The nitro and OH are trans here. The nitro and OH are cis with respect to each other. So this is called the Z isomer and this is the E isomer of the compound. When the europium shift reagent is added, it is going to complex to the most basic site, which is this particular oxygen here. And with respect to this oxygen, if you look at, when the europium is complexed here, the methyl group is cis with respect to that particular europium complexation site. Whereas here this would be trans. In other words, the distance between the europium, oxygen and the methyl will be much larger in this Z isomer compared to in the case of the E isomer. So the Z isomer, because the distance is much larger, should show a smaller effect in terms of the induced chemical shift value to the europium concentration. As you keep increasing the europium concentration, more and more complex should be formed, and the chemical shift value of these methyls, two methyls, should keep increasing as you increase the europium concentration. But to what extent it increases is decided by the slope of this particular curve. The one with the larger slope, if you look at, for example, the methyl group which is cis with respect to the in other words the E isomer, where this is the E isomer where the OH and the NO2 are different, but the methyl is cis to the OH. The Z and E are determined between the NO2 and the OH group, but if you look at the methyl and the OH relationship in the E isomer, that is cis with respect to each E isomer. So the E isomer should give the strongest effect in terms of the induced shift as increase the concentration of the europium, whereas the Z isomer, where the methyl and OH are trans with respect to each other, gives a smaller slope or smaller slope with respect to the E isomer. So when you have both the isomers, if you determine the relative slope of these two curves that are seen here, the one with the larger slope obviously belongs to the one where the europium and the methyl coordination, the europium coordination and the methyl are cis with respect to each other, which is the E isomer in this particular case. One can also use the chiral shift reagent along with the Mosher-Stahl to differentiate between the diastereoisomers. In other words, a diastereomer mixture of ester is formed. In addition to that, europium is also ordered to increase the shift. Where the resolution is not so good, you can also add the europium. Europium will essentially complex to one of these basic sites here and induce a large shift between the diastereoisomers. So the SS isomer is a minor isomer here, whereas the RS isomer is a major isomer in this particular mixture. Whereas if you take the opposite mixture, namely the SS being smaller here, whereas the SS being higher here, the ratios, the integration ratio tells us that this is the ratio of 179:23, whereas this is in the ratio of 185:10 as far as the two diastereoisomers are concerned. Here a combination of Mosher-Schuster along with the europium F43 is used to distinguish and separate the two diastereoisomer signals in the NMR spectrum. On the other hand, if you take a racemic mixture, you get 1:1 signal intensity ratio for the racemic ester along with the europium F43 being added to the mixture for the separation of the signal. So what we have seen in this particular module, which is a brief module, is that stereoisomers can be distinguished by one another the stereochemistry can be distinguished from one another by comparison of chemical shift as well as coupling constant value. This was done in the previous module. Relative configurations can be established, comparison of the J value. This also we saw in the module 11. NOE difference spectroscopy can be used for determining molecular geometry and stereochemistry. This we saw in this particular module. A chiral lanthanide shift reagent can be used to distinguish diastereoisomers, and chiral lanthanide shift reagents can be used to determine the enantiomeric excess of a mixture. And of course, the Mosher's salt method, Mosher's ester method can be used for distinguishing enantiomeric excess of compounds in a racemic mixture or in an enantiomerically excess compound. It is possible to distinguish them by NMR spectroscopy by forming the diastereomeric mixture of esters using a Mosher's acid chloride. Thank you very much for your attention. Once again, I would like to recommend these books for the stereochemical aspects or the NOE effect and so on can be learned from these nicely written books. Thank you for your attention once again.